A talk that is very short and it is accessible to extremely broad audience, and I should talk about my very recent research. So combination of all these three factors together is really demanding. So he is my boss, he will be my future boss, so I will try to do my best. So we did some research on real-time dynamics of complex quantum systems. So, okay, what will be the rule for this presentation? So, the rule for this presentation is that uninformed audience should understand what I tell, and experts, and believe me, they are really top-level experts, top-level world experts on the quantum statistical physics in this room. They will not tell me that I am wrong. So this I will try to achieve. Okay, so let me start with something very general. So in physics, we have something like standard symbols. So for instance, we usually use letter V for velocity, X for position, E for energy, and almost always we use T for time. But if you go to solid-state physics, in the solid-state physics, you have something like the Hubbard model, and it is really the standard model of solid-state physics. And in this standard model, we use letter T for kinetic energy. And it is very informative that in solid-state physics, for many years, we were not interested in time-dependent phenomena. Otherwise, we would not use this letter for the kinetic energy. So things changed more or less 10 years ago, and there are something like time-resolved experiments, very modern time-resolved experiments. Now T is again time, and we use letter J for kinetic energy. Okay, so let me tell you what we study in these new experiments. So the main problem is, it sounds simple, it is thermalization. So imagine we have a system of qubits, exactly the same system which was described by our dear guests. So we have, let's say, L qubits, so each qubit can have state up or down. So you can think that qubits are arrows. It is not good definition. The arrow can point either up or down. It is not good definition, but maybe for this talk it is enough. So in order to specify the state of the system, we need a lot of data. So we need, if we have L qubits, we need 2 to power L real numbers or complex numbers in general. So we can think that in such system we can really write really such huge information, so many independent parameters. But now what means thermalization? So thermalization means the following, or it is the consequence of thermalization. So take the system to be very large, and we try to measure something. Whatever you think would be okay. Kinetic energy, current, momentum, whatever quantity, it would be okay. So if we do these measurements initially on this quantum state, our result will depend on this amount of parameters. So it will depend on this on this information which we store in our system. But now wait very long, and measure again the same quantity, and you will find out that the quantity at the end depends only on one parameter, and this is temperature. So this is the very broad thinking of what is thermalization. So this is information loss, or maybe let's say the consequence of thermalization is loss of information. The opposite is not true, to be strict, but in this way we can think about it. Okay. So what we can, so this is the challenge, most challenge in the studies. So what we study? So the obvious thing is, look, here we can store some information in the system, and this information is lost in time. So what we try to do, we try to avoid thermalization of the systems, and this is one part of our research. And the second part of our research is something different. It means we really observe in experiments thermalization in very complex solids, like in superconductors. So in these materials which are used to build D-wave, and from these experiments we try to answer questions which we were unable to answer before. So I would like to go quite briefly through these two problems. Maybe if there is not enough time, I will stop only after the first problem. So maybe this is this lecture was assumed to be accessible to extremely broad audience, so I avoided powers. So let's assume that we have a system of L qubits, and we want to calculate what is the evolution of such system in time. Of course, we can do it with classical computers, and what we have to do does not seem to be very complicated. It is standard matrix vector multiplication. With the only problem is that these matrices are huge. So for L qubits, we need matrices which have this dimension, so 2 to power L times 2 to power L. So for what we can study in one-dimensional systems, if we are interested in thermalization of the spin systems, so that this, let me maybe say again that D-wave is one example of the spin system. So we are slightly more general in our studies, but one particular example is exactly D-wave. So in order to calculate evolution of 30 qubits, we would need to store as many numbers, so it will be 1 followed by 18 zeros. But if we want to study exactly what is the evolution of 1,000 qubits, then we need this number, so it is 1 followed by 300 zeros, and it's clear that we don't have such computers, and it's clear we will not have these computers, probably classical computers ever. Yeah. And I mentioned you about the standard model, so in the standard model in the solid state physics, the Hubbard model, in that case you would have to multiply the number of 0 by 2. So you would go to 600 zeros. Anyway, so still we are not completely, we still can do something. So the tricks which physicists learn is how to select the most relevant elements. And it takes years of study what means the relevant elements out of this huge number of elements. Okay, so now just briefly how we can avoid thermalization. So again, what is thermalization? Thermalization again is that if we measure some quantity at initial state, and we could make many measurements, then these measurements can encode huge number of different parameters, but after a long time we lose all this information and we are left with only single parameter with temperature. Why it happens is that maybe it's not obvious, but most generic systems, it means systems which we have in our surrounding, they remember only single quantity, usually, this is energy. Maybe 2 quantities, like energy and number of electrons, maybe 3, but not more. It means that if we have 2 qubits, or let's say 5 qubits, in these 5 qubits remember 3 quantities. If we go to million qubits, we would still remember only 3 quantities. But there are special systems, and this was the subject of our research. And these systems, if we have a system with L qubits, so sites means qubits here, the system would remember L quantities. So this is very, very, very nice, because it is big hope that maybe in the future we could use these systems to store quantum information. Okay, so what is how we can observe that the system which we deal with belongs to this special group of systems which, they remember many quantities. We call them conserved quantities. This is analog to conservation laws in the physics. So we have conservation of energy, conservation of particle numbers, and there are some other conserved quantities. How we can observe it? It seems not to be very complicated. Let's assume that we have, let's make the plot. So this will be force and it will be time. And how there is no force acting on our system long time ago. Then suddenly we turn on the field, so the driving. One can think the force. The force is constant, and then we turn off the force again. So the generic systems which are in our surrounding, they behave in the way that as long as we drive the system, there is current or there is velocity. But if we stop, if we turn off the field, the velocity or the current drops to 0. So that's quite clear. We have a car, we push the car is moving, we stop pushing, the car is stopping. But these special systems behave in a different way. So maybe we don't need to discuss this initial part, but once we stop the force, the velocity drops down but stays non-zero. And this is very nice that you think that you push your car, you stop pushing your car, the car slows down but does not stop. It's not stopping, it's still moving. Okay, so what we managed to show is that these magic additional conserved quantities, they fully determine this non-vanishing component of the current, so it was our achievement here. And then we realized that we studied, I think it is probably the best studied model in the solid state physics. It is the Heisenberg model. And in the Heisenberg model, we found that what we have proven here exactly is violated. So either we were totally wrong, or what turns out they are new, unknown conserved quantities. But it was not very likely because people spent many years studying this model. But still, at the end, it turns out that we found these new conserved quantities. How we did it? Usually, up to this moment, people used pure mathematics to determine these conserved quantities, and this mathematics is extremely complex. There are only few groups in the world which can develop this mathematics. I mean, many people know it, but only few groups know how to really develop this formalism. But what we developed numerical algorithm, and it was developed in such a way that it generates all conserved quantities, so all this Qi, and we really found that before we ran this algorithm, people knew only half of them. So this is nice. So this is one connection about non-thermalizing systems, and there is algorithm which generates these quantities which cause that the information, quantum information which is stored in the system does not decay. Okay, and briefly, because the lunch is coming, the second, I think also important problem we know at the end that the D-wave machine is built out of superconductors. And let me tell you the very basic idea about superconductors. So what is important, these superconductors are Cooper pairs. You probably, most of you probably heard about Cooper pairs. They consist of two electrons, but usually electrons repel. So there is something magic, some magic glue, which causes these two electrons to come and stay together. And it is a big puzzle in the research on superconductors. What is this glue? Especially in the research on high temperature superconductors, like the name of D-wave, I think I can tell that it comes from something that is very well known for high temperature superconductors. And anyway, so we have two possibilities what could be this magic glue. So this magic glue could be some magnetic glue. How you can think about magnetic glue? Magnetic glue would again be some degree of freedom like qubit that can point either down or can point either up. But there is also something that we call the standard glue. So this is what we know in standard superconductors. I will not need to mention more, but there is a big distinction. So here we have two possibilities, and in the standard glue we have more than two possibilities. So the obvious case is, okay, let's go and try to excite this higher energy states. But there is a problem. At room temperatures, our system usually is in this low state, in this lowest state. And if we want to populate these upper states, we need to heat the system to huge temperatures, like 1000 kelvins. But this is not good for crystals because they will melt and these excitations will vanish. So we cannot heat the whole system to check if there is something above these two levels. So what is the idea in these new experiments? We cannot heat up the whole system, but what we can do, we can heat for very short time, not the whole system, but only this glue. And this is the biggest achievement of these new experiments. So how it happens, this is the slide from, there is a slide from this web page, so this is not, I haven't done it. Anyway, here the blue arrow is what we did usually before, so we applied some laser pulse. This pulse hit the sample. It is some part of this pulse is reflected, and we measure this reflected photons, and from this we learn a lot about the sample. So this new idea is that before we do measurement, we apply one extra pulse. This is we called pump pulse. But what is the challenge? The challenge is the distance between the first pulse and the second pulse, and this is 10 femtoseconds. So 10 femtoseconds, it is 0. Then we should have 13 zeros and 1 at the end. So one should be smart how to make such tiny delay in time. Okay, without going, maybe one detail why it works. So it works like this. So we have system where we have a lot of electrons. We apply this pump pulse, and this pump pulse just hits few electrons, and these electrons go to states with very high energy, and then they go down, so they release their energy to this glue. And during this process, when the electrons go down with energy and hit the glue, we have a unique possibility of observe what is going on with this glue, because we just hit it to huge energies. The sample, the total sample is cold, but this glue we call them bosons. This glue is hot, and we can observe, we can learn something new about this glue. And that was our main finding, that for this most fancy superconductors, high TC superconductors, this glue is of magnetic origin. So we have only these two possibilities. Okay, so let me come to this conclusion. I think that the lunch is waiting, so I should not speak longer. So what we are doing at present, so we try to use the most powerful classical computers, and from this we try to learn the properties of qubits, how these qubits evolve in time, because at the end it is how D-wave is operating, yes, that the system of qubits, interacting qubits, this is the challenge, it evolves in time. And yeah, we also learn using these computers how to build advanced materials like superconductors, which are then used to assemble these qubits like Josephson junctions. But if you think at these two pieces, this knowledge about operating of qubits and the knowledge about building these advanced materials, all this together, it makes the quantum computer. So what is the future is just to skip this not so powerful classical computers. Maybe we will use quantum computers to learn about quantum computers. Okay, thank you very much for your attention.